Okay, thank you.
Gianni, before you start the lecture, we would like to present you a memento from ICTS for this for giving this lecture.
Thank you very much. Thank you. Well, the air conditioning is not on, so I will take out my jacket. This morning was quite cool. And in fact, my voice is lowered. Okay. So, well, let me say that I am very honored to give this lecture because, many years ago, I read the biography of Ramanujan. It was a very interesting, detailed biography, which exists in English. Now I don't remember the author. And I was very impressed by his story. And so I read also the famous mathematician Apology of Hardy, who had been his mentor for when he went to England. And so you see, you read these biographies of these important scientists of the past, and you don't think that someday you will be connected. And so of course, I mean, I'm a theoretical physicist, but I did some mathematical work in stochastic processes that mathematicians have appreciated. So, I mean, I can, it's not entirely unjustified that I am here. Okay, today I will tell you, I mean, this is a colloquium. So maybe you want us to lower the... You see, a colloquium is supposed to be something more relaxed than a technical exposition. So I will try to entertain you in some way about a subject which is not very entertaining otherwise. So I will discuss only essentially some very general ideas and put them in some historical perspective. Okay. As Stefano mentioned, we are a small group called by Derrida the Italian team, even if one is Brazilian. And he said they are all mathematicians. Well, the bad point is that 3 of them were my students, so there was some degeneration with respect to the original. They were students in physics. And these were Lorenzo Bertini long ago, and then Davide Gabrielli and Alberto De Sole, who by now has become a very well-known algebraist of international reputation. But he still continues to work. So with this Italian team, we have obviously now different competences, and that is what has helped us to go on for 15 years, finding and proposing some new things. So let me, you see, in the abstract that I gave, I emphasized that non-equilibrium is everywhere, is ubiquitous, and covers all the most different situations. But it is a subject that has resisted for a long time. And in fact, also you find many, sometimes, usually physicists have a very good intuitions, but sometimes also wrong statements have been advanced. I mean, is a part of physics which is not terribly intuitive. And, but however, in the last 25, 30 years, there has been considerable improvement in the understanding, especially because there were some simple mathematical models that could be treated in a rigorous way. And that has been really a turning point in this game. So far, I mean, usually one uses concept of equilibrium, thermodynamics, and I will show you that one near equilibrium, essentially, this is enough. But sometimes they are used even beyond their range of validity. So let me give some example of non-equilibrium situation. A hurricane is a rather violent non-equilibrium situation. However, I mean, you can go to astrophysics, and galaxies are non-equilibrium situations. They are more or less in a stationary state, but they lose matter from their arms, and it's a complicated situation. And generally speaking, the universe is not in equilibrium. I mean, it's expanding, and the theories of the origin of the universe, like a Big Bang, they start with something even more violent. Well, a domain of non-equilibrium which now interests very much physicists is biophysics, and especially the molecular motors, which were discovered, I think, at the beginning of the 80s. And it's a very good subject for making models. And in fact, many of the models that have been discussed also already in this room have also been adapted to describe molecular motors. What are molecular motors? They do all sorts of services in living matter. So, and they can have, very different shapes. You see, they can be like some athlete in a circus which walk on an object which is called a microtubule. Or maybe what they do, these molecular motors, they transform chemical energy into mechanical energy. So that is what unites this subject. So and typically in non-equilibrium situation, and they exploit also fluctuations which exist in. For example, they are very specialized. For example, when the double helix is separated, there are molecular motors which do this work. So this is in fact, I mean, many physicists have introduced models in the last decades. And you see, when I raise my arm, these are billions of molecular motors which do the work. And there is a special molecular motor for muscles, which, so I mean, in every situation, biologically important situation, then, for example, tectonics, I mean, the fact that you have movements in the Earth crust is a typical non-equilibrium situation, and people in the sciences of the Earth know it very well. This is the famous California. I don't know what is the English name. Yeah, St. Andrew is the name of this. But then you may have explosions. And this is also, and one would think that it would be very difficult to make a theory of an explosion. But I mean, for example, there have been famous Russian physicists like Zeldovich, who developed a thermodynamic theory for explosions. And you find also in Landau-Lifshitz. And so you see, you have an enormous variety of phenomena, and you understand immediately that it is not possible to cover with only one theory all the situations. The situations out of equilibrium are much more rich than what you have in equilibrium. In equilibrium, you have phase transitions, but that nothing much. It doesn't happen much more. You have critical phenomena, which are interesting. Okay, so so this concept. How much time do I have? 1 hour. Oh, so this takes into account when I started. Okay. I mean, the rule that we have, but then rarely is followed, is that for a colloquium, the first 20 minutes, they have to be understood by everybody. The second 20 minutes by people with some scientific background. And in the last 20 minutes, one can inject something for the specialist, but not necessarily. Okay, so the equilibrium and non-equilibrium are both mechanical and thermodynamical concepts, and here we are interested in thermodynamics, because we consider always systems with many degrees of freedom. So this is the situation of classical thermodynamics. Classical thermodynamics does not consider, never considers non-equilibrium situations. However, I mean, that is, it ignores something which conceptually is important. Because you see, even when you classical thermodynamics consider very slow transformations. However, in order that something can happen, the system must go a little bit out of equilibrium, otherwise nothing happens. This was emphasized. There is a very good book in classical thermodynamics by Callan, so which emphasizes this aspect, especially in the last, you see, the quasi-static process simply is an ordered succession of equilibrium state, whereas a real process is a temporal succession of equilibrium and non-equilibrium states. So, however, I mean, you see, classical thermodynamics is not able to clarify its own foundations because you need some non-equilibrium theory. But I mean, it was formulated, so it was also socially motivated by the first industrial revolution, and it formed the basis for producing engines and machines that were used in the first industrial revolution, which was based on essentially machines on steam, based on high pressure steam and so on. So the first principle of classical thermodynamics was the recognition that heat is a form of energy, and in any transformation, the sum of work and heat is the total energy which is exchanged. Okay, the second principle, it has many formulations. One, for example, is that heat will never flow from lower temperature to higher temperature. But, however, I mean, from our point of view, we prefer the abstract formulations introducing the entropy. So the second principle can be stated in this way, and the equilibrium state is the state of maximum entropy. There is a third principle, which is the so-called Nernst heat theorem, but it is not interesting from our point of view. Okay, now entropy, in fact, is not a very intuitive concept. And if you try to read the original papers by Robert Claudius, the first reaction that you have is, how did he think of it? I mean, in fact, I mean, I was, but then I read his, known as his fourth memory, and then he explains how, and you see, he wanted something which some number which characterizes, for example, transformations which can be physically very different because they are done, for example, with gases or other type of materials and so on. But the trace that they leave in the world, in the environment, is exactly the same. So you may have a Carnot engine or an engine made of other things, but which releases the same quantity of work and the same quantity of heat goes from higher temperature, lower temperature. And he wanted to characterize these two transformations in some way. So he was looking for an invariant going from one type of transformation to another one. And that is, then presumably he calculated it for, he guessed it for ideal gas, but then he understood what was at stake. In fact, I advise you to read the fourth memory that you find also on the web of Clausius, because at some point he edited all his works with comments. The comments sometimes are longer than the memories themselves, but it's very instructive. And this exists also in book form, I think, in French and in English. So, as you know, the statistical interpretation of entropy was given by Boltzmann. And however, Boltzmann never really wrote exactly this equation, because he was working with what is called Boltzmann entropy, which is what is discussed with the famous H theorem. And then the constant that he had in front of this logarithm was not the Boltzmann constant, but was the gas constant, and he limited his consideration to gases. The man who really understood the universality of this relationship was Planck. And in fact, it was written in this way for the first time by Planck, but without that constant. Because Planck said, okay, that constant was usually added to all thermodynamic functions. And this constant made the relationship between entropy. And this, what is called thermodynamic probability, is the number of microscopic states that correspond to some microscopic parameters. And so in Planck form, this constant, it disappears. And that was an important step on his way to quantum theory. Now, there is also another definition of entropy in information theory. And as you know, this is connected with the probability of the characters or word of a message. And however, there is this story that apparently von Neumann, which suggested the name to Shannon, the comment was that you should call entropy for two reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name. So it has already a name. In the second place, and more important, no one really knows what entropy really is. And so in the debate, you will always have the advantage. So that is the situation. And why I spent so much time on entropy? Because, I mean, now, what are the non-equilibrium states which are closer to equilibrium states? Closer conceptually, in the sense that they do not depend on time. But you may have situations where which are very far from equilibrium, but I mean they are stationary, so there is no time dependence. And so the simplest example are, for example, an iron bar, rod or bar between two sources, heat sources at different temperatures, or it may be when you have a flow of chemical substances and you have differences in chemical potentials and so on and so forth, or difference in electrical potential, so you have a flow of charges in a conductor. Okay. The interesting thing is that stationary states, so the first question that you would like to answer, for stationary states, can we develop I don't want to call it thermodynamics because certainly will be different, but let's say a macroscopic theory, a self-contained macroscopic theory, in the same way as you have one for for equilibrium states. Actually, this has been, at least in my mind, has been always a motivation to see whether a self-contained macroscopic theory could be developed, and that is what we. So, for example, I mean, as soon as you go out of equilibrium, you have the fluctuation exhibit new features. For example, and this is experimentally observed, the space correlation of density extend to macroscopic distances. So even usually correlations decay exponentially in an equilibrium state. Now here you have correlations which remain go up to the macroscopic scale, and so the situation has, and this has been noticed by many people in these years, somehow resembles the situation of the critical point in the theory of phase transitions. Now, the typical setting for a stationary state, you have you have a system which is in contact with several reservoirs, which may be chemical substances, heat, and electricity, and so on. So that is the situation that for which one would like to construct some self-contained macroscopic theory. Now, what is the and I will speak with some length about this problem. You see, if you want to imitate thermodynamics, you would like to introduce functions of state, like entropy, free energy, and so on. However, I mean, it's clear that this is, you can say that from the beginning, that since the system is in contact with an environment, typically, whatever quantity you introduce will depend on the environment. So in general, there will not exist quantities which depend only on the state of the system. So the situation is more complicated. Now, in all these years, I would say that the leitmotif has been the study of fluctuation. You know that there have been many formulations of what are called fluctuation theorems. Well, most of them have been formulated for systems with a finite number of degrees of freedom. So they are not really thermodynamic relationship, but you can extend. Many of them can be extended to the infinitely degrees of freedom situation. Now, you see, when you are near equilibrium, you don't need to think about this problem, because you make, for example, you take the entropy, and this was the principle of Onsager theory in 1931, which has been used so far for 80 years, even in situations where it was not really applicable, but since there was nothing else, this is what physicists did. And you see, in the case of, sorry. No. In the case when you are near equilibrium, you can, I mean, you can always use the equilibrium entropy, because the first part, okay, is that is the maximum entropy. If you are near an equilibrium state, S bar is the maximal value for the entropy. And then, I mean, the deviations from equilibrium you can study in terms of this, of first order and also second order derivatives. Now, but the situation we want to describe is the one in which we are really far from equilibrium in a stationary state. Now, I will discuss in some detail a paper that Einstein wrote in 1910, because this is something that I discovered along the way. So when we were halfway in trying to formulate this microscopic fluctuation theory, a name which we introduced in the second of our paper. However, to this theory, many people have given very important contributions. So it's not a field of our, which is only ours. I mean, because why I'm discussing Einstein? Because Einstein was the first to develop a theory of equilibrium fluctuations, and he wanted to explain the opalescence of fluids. Then this work is not one of his best known, because while the first part of the paper is very beautiful, the second part is wrong. And so it was violently attacked by Einstein and Zernike, who said in a published paper, if you follow Einstein, you will get nowhere. So, but anyway, well, Einstein wrote many wrong papers, but that, as you see, it doesn't, I mean, for somebody today, this would damage seriously his career, but not in this case. So he developed this macroscopic fluctuation theory for equilibrium states, and it was really the first case I know of large deviation theory in physics, in statistical mechanics. Now, why I want to explain Einstein? Because what I realized, not at the beginning, but more recently, our way has been somewhat different, but that what we have been doing and what people have been doing studying macroscopic fluctuation theory is exactly the same way that Einstein, but going the other way, going the opposite way. Now I will explain all this, because it doesn't require much technicalities. So you see, his first judgment on Boltzmann was somehow quite hard, because he said, okay, this number of microscopic state compatible with the macroscopic parameters are very complicated to calculate. For every different system, you need a different theory. So he didn't like it at all. So his first reaction was that, considered from a phenomenological point of view, equation 4 appears devoid of content. So that's quite sharp. Now, And then he tried to remedy this and said, okay, via ergodic theory, you can actually give a meaning to this macroscopic probabilities, because for every choice of macroscopic variables, you will have different microscopic states. And so, I mean, if you can make, at least in principle, an experiment where you wait a very long time and you determine the fraction of time that the system spends in each of these state, and then the ratio of this time with respect to the total time in ergodic theory is just the probability of that macroscopic state. So, but then he put aside the question. And now then he started developing this theory of, to arrive at his theory of opalescence. You see, because the physical interpretation of opalescence is that you have, in the fluid, you have fluctuations of densities, for example, of macroscopic variables due to the, I mean, thermic effects and so on. And so in each point, the state of the system is different. And so because it fluctuates with respect, for example, for the flat profile that you have in a. Okay, so you see, all these slides are quotations. So, so you see, he took advantage of this constant to normalize in some way this number, and clearly S minus S0 is the state of maximum entropy, so this exponent is negative, and so he wrote this probability distribution, which is clearly a large deviation estimate. As you see, and is Avogadro's number, so it's an enormous number. So he interpreted the Boltzmann formula as a large deviation formula. As far as I know, this is the first application I know. Then, however, besides that paper, well, then he goes on and makes explicit calculations, and but then he thinks that this theory can be valid also at the critical point, and that was wrong, because at the critical point you have long-range correlation, so you cannot think that every point of the system is independent statistically. However, there is a very interesting paper, which is not included in his collected paper in English, which was a seminar that he gave at the Zurich, at the Swiss, at the Zurich Physical Society, and which, well, I don't read German, so I read it for the first time in 2005 when Duplantier translated it into French for the celebrations of the 100 years of relativity and Brownian motion and so on. So he, again, he formulates his doubts about the usefulness of the Boltzmann formula. And as you see, he says that, I'm sorry, it's in French, but I didn't retranslate it into English because then, but I hope you, most of you can read it. Okay. So he says explicitly that the Boltzmann formula must be used to calculate probabilities, because we can put our hands on entropy thermodynamically, and this is a very good formula to calculate probabilities. But then he went on and made an application, which is an application that now I recognize. I will explain Einstein. the path that he followed is exactly the one that we have followed in the reverse direction. Because he combined this formula with hydrodynamics. You see, he considered the case you have a fluid at rest, and then you have a small sphere which falls down, and I mean, in its equilibrium state, it's on the bottom of this system. However, there are thermal fluctuations, so sometimes this sphere will jump and will reach some. And so he applied the Boltzmann formula, seen as a large deviation estimate, and this is very simple because the energy, there is only the gravitational field, so this is the formula, and this was in fact experimentally confirmed by Perrin. But then that is the application. He derived the law of the Brownian motion thermodynamically, because so in a different way with respect to the 1905 papers, and then you see, he used the Stokes law. Stokes law tells you what is the speed of a sphere immersed which is heavier than the fluid in which it is immersed. It reaches a stationary velocity, which is given by a famous formula due to Stokes. It is the viscosity. P is the radius of the sphere, and mu is the level, the height of the. Then he says, okay, this particle, this small sphere, will have fluctuations in this movement, in going down, and then he tries to calculate these fluctuations, and he assumes that these are that this fluctuation has zero mean, and also that the displacement and the microscopic displacement and the fluctuation are independent variables. And then you see, he calculated the variation of the stochastic displacement, and he found that it was proportional to the time. So, and this was the law of the Brownian motion. Now, however, it's clear that you can follow this path in the reverse way. You could start from hydrodynamics, then you add some noise, and then, I mean, Gaussian noise, because there are many reasons to add to hydrodynamics Gaussian noise, what is called fluctuating hydrodynamics, because, and the arguments are based on central limit type theorem, I mean, the qualitative arguments. And then you, so it's easy to calculate large deviations for a Gaussian variable. So, and you go back, and you go from fluctuating hydrodynamics to a large deviation formula. So, and that is essentially the logic of what has been done in all this, in all these years. So, now the case the case that Einstein considered was the case of an isolated system, which did not exchange anything with the. Now, in order, what was interesting in this calculation was the fact that the exponent of the large deviation estimates was a thermodynamic function. So, if you want to know what is the analog of this thermodynamic function out of equilibrium, you can you have to understand what is the physical meaning of this exponent. I mean, if you stop at saying that it is the entropy of the free energy, you don't go very far. But you know that it has a physical meaning. And this is, for example, discussed well in Landau-Lifshitz on statistical mechanics. And then what is the meaning of this difference, this deviation from the maximum entropy, which is at 0? I mean, if you apply, we are in equilibrium, so we apply thermodynamics. So F is the Helmholtz free energy, and this quantity represents the minimal work to bring the equilibrium state to the state corresponding to F at constant temperature or volume. So suppose you have a volume, and then part of it, the density changes, and you see a different value for the density. And then, I mean, this quantity represents the minimal work that you have to do to create such a fluctuation. Vice versa, when you relax the fluctuation, is the maximal work that you can get out of it. And that is what is called availability by engineers. But it's a word which is unknown to physicists. So, but for them is important. So once you understand that this object represents a minimal work, you realize that the concept of minimal work is meaningful also outside of equilibrium. So if you have a stationary state and then you have a fluctuation, then you can ask what is the minimal work that you need to create such a fluctuation. Okay? And then, in fact, however, the quantities, you see, when you calculate the entropy, usually you use the specific heat, I mean, quantities related to the equilibrium physics. When you are out of equilibrium, you don't have such concepts, and then you have many more general situations. However, you have the so-called transport coefficients. And so you have to understand how to calculate this minimal work in terms of these macroscopic quantities. Okay. Now, the macroscopic fluctuation theory is not a theory which covers everything, but has been conceived, I mean, because the situation is simpler for diffusive systems. And then we shall see what does it mean. So, as I said, we want to go from hydrodynamics to large deviations. And you see, first of all, in non-equilibrium, in a stationary situation, you must be able to define thermodynamic variables. And since usually, for example, you will have a profile of temperature between two temperatures, or a profile of densities, this means that you need to define locally these variables. Otherwise, you cannot start your game. So this means that locally the system is at equilibrium, or slightly deviates from equilibrium. Then you may ask, but then how can I treat situations in which, for example, are very large difference? Well, the point is that locally you deviate very little from equilibrium, but summing many small deviation from equilibrium, you can reach a very large non-equilibrium situation. So locally is in equilibrium. Globally, in fact, I mean, the hydrodynamic evolution times are much longer. So local equilibrium means that the system locally reaches equilibrium in a time which is much shorter than the macroscopic time that you are considering. And in many models that have been proposed, like the simple exclusion and others, you can prove that local equilibrium, in fact, is true. So you had then, and also you can prove hydrodynamic equations, and I think one of the first work was done by Stefano with Varadan and Kipnis also, which was a model for much of what happened afterwards. So what is the formula? Suppose that we consider a case in which there is a conservation law. Actually, the macroscopic fluctuation theory can be developed also for reaction diffusion situations, and there is no real difficulty. But the case in which you have conservation laws, it's very interesting. So, you have a conservation law, so it connects the density with current, and then you have to give a thermodynamic expression for this current. And this is what is usually called the constitutive equation. And you see, locally, because this is what is called the linear response regime, but that is what interests us locally, because locally we are always very close to equilibrium. And so there are two terms. One is connected with the gradients that are in this place, and then you may have an external field and a variable which is called the mobility, which in general may be functions of thermodynamic variables, and which is proportional to the field, which must be a weak field. Now you can give a precise meaning to all this by discussing these particle models. And that is really the great conceptual advance that we had. And this characterizes diffusive systems, because you see there are no inertial terms which depend on there is no kinetic energy part or momentum part and so on. I mean, actually in a real system, in a gas of real particles, you have at least 5 conservation laws, because you have energy, 3 components of momentum, which makes 4, and what is the mass? Yeah. Okay, it's clear that your theory must cover also the equilibrium. Equilibrium is a special case, and in fact it does. But anyway, what I want to emphasize here that these are the transport coefficients, and these are measurable quantities. I realize from the literature that they are not easy to measure. This chi is what, when you have no row dependence, is what is called the Onsager matrix, which has some symmetry properties and so on. Now, let's go on. And in fact, to cover also the equilibrium case, this can be done because there is also a relationship which connects the two transport coefficients, and it relates them to their ratio is connected with the second derivative of the free energy, equilibrium free energy density. Also, this relationship is called the Einstein relationship because, well, in the simple case of the Brownian motion, he derived it. But anyway, you see, so locally there is a connection which is mediated by the equilibrium free energy. Okay. Now consider a system in a stationary state. So there is a time-independent solution, which, for example, may be think of the Fourier law, maybe a linear profile of temperature or a linear profile of densities, and then suppose that due to one of these stationary state fluctuation, your density goes out of the stationary value. So it's different from the rho bar, which describes the profile. So, and suppose that this is the initial condition of a trajectory, which has nothing to do with the hydrodynamic trajectory. Then, so you have a situation in which first you create a fluctuation with respect to the profile, the stationary profile, and then you get also, you have also a fluctuation in the current with respect to either the hydrodynamic value. Okay, and then and the two things must always be connected by the conservation law, because this also. Now, so the cost of this fluctuation will consist of two parts: the cost necessary to create the initial condition and the cost necessary to follow the trajectories, this trajectory. So now the first term, so the cost to create the initial condition, we call V of rho in general, and in non-equilibrium represent exactly the analog of the entropy or free energy. It will be very different. I will give you an example in a moment, and this is I mean, one way of calculating it is by extending to infinite dimensional case what is a well-known theory of fluctuation in dynamical systems, the Wenzel and Friedlin theory. But anyway, let me discuss the structure. And it's very different from the equilibrium case, because equilibrium is a local function of the density, but out of equilibrium you may have this long-range correlation, so in general it's non-local. Now this has to be calculated, and the calculation is longer than for V, and this is the final answer. And so you see that this is the power dissipated by this extra current, the difference between the fluctuation and the current of the hydrodynamic current. Chi minus 1 is the inverse of this mobility. And then, I mean, this is very simple to interpret. This quantity, I mean, this double integral is nothing but the total power dissipated during the time in which you follow this trajectory. And in fact, is the, you see, chi minus 1, the inverse of the mobility in the case of an electrical circuit is the resistance. And this is the power dissipated according to Ohm's law. And so now there is this factor in front, which is correct, but which is, you have to split it into 1/2 and 1/2. 1/2 is due to the fact that you are dealing with the Gaussian stochasticity, and the other at the origin of the fluctuation, and the other half is connected with the definition of transport coefficient. So, but anyway, I mean, this is. So let's go on. And so now we use the Markovian hypothesis. You see, that is the terminology that you find in Cullen book or in other thermodynamic books written half a century ago, in which if the current depends locally on the, locally is not important, depends on the thermodynamic variables at the same time, so there is no delay, then it's called Markovian evolution, no matter what happens at the microscopic level. And so you see that the total work that you have to do to create such a fluctuation and then follow the trajectory, this is given by a first term, which is the analog of the free energy or entropy, and this part here, which is this dynamic formula, which has a very simple interpretation. And I think that the validity of this expression goes beyond the minimal, diffusive systems, because actually what characterizes the system is this expression that may go well beyond okay, so. And so, I mean, you see, this probability is the product of two factors, one associated with the, and this epsilon is, what is it? Is a typical intermolecular distance, is a ratio, if you want, of a microscopic distance, to a microscopic distance. And So this factor epsilon to the minus d is what takes the place of the Avogadro's number. And these are these rho epsilon j epsilon are what are called empirical density and current, corresponding to a coarse grading over a small macroscopic volume. And these quantities clearly depend on epsilon. Okay, so this is the basic formula. All the macroscopic fluctuation theory follows from this formula and nothing else. And that I will, I mean, in the pedagogic lecture, I want to give some idea of the derivation of this and how everything follows, not only from this formula, but from this formula plus time reversal. And in fact, you have a very clean way of discussing time reversal in this context. And so, and then we shall see that, in fact, for those who will come, that this non-equilibrium free energy can be obtained from this dynamic functional through a variational principle, which, if you want, takes the place of the maximum entropy principle in equilibrium statistical mechanics. There is also a differential equation that you can write for this V, and which can solve it in a few cases. And I will explain in the other lectures the solution. But the nice thing, so let's write this for the simple exclusion process, which I think is known to most of you. And so you see, I have inserted the mobility of the simple exclusion. The diffusion coefficient is 1, and can be reduced to, in 3 lines, to nonlinear differential equations. And this nonlinear differential equation was discovered for the first time by Derrida, Leibowitz, and Speer. And but by solving by, if I want to say by brute force, the microscopic model, calculating the distribution, the microscopic distribution of the particle system, and we discovered that we were on the right way when we were able to derive this equation from the Hamilton-Jacobi equation in 3 lines, while their derivation required 40 pages. So, and now, for example, for the simple exclusion, you get this explicit expression. This is the equilibrium part. And then you get this extra term, which is clearly non-local, because when you solve for this function phi, you will get a very non-local function of the density. And so this object here is highly non-local. And well, there are, my time is almost finished, so I have many other things to say, but it doesn't matter. There are very interesting results, especially in the study of current fluctuations. But this I will do in the lectures. But for example, just to give you an example of a situation in which you have phase transitions which are impossible in equilibrium, but are possible out of equilibrium. So, and this manifests themselves in the fact that this V, for certain values of this profile rho, may become non-differentiable. So the situation, and but I will not explain anything now, it's, you have forget about the upper diagram. You see, because thermodynamic functions for reasons of stability have to be convex. But if you have non-differentiability, for example, you may have a first-order transition far from the stationary state. And this we discovered and we proved, actually, some 6 years ago, that in fact, for the simple exclusion, when you have the boundary conditions which are opposite to the external field, so they act in opposite ways, they produce currents in opposite ways. In this case, you have such a transition. You can evaluate, prove that. Then these things have been, there was a follow-up by Caffrey and other in Israel, but it was numerical. They discovered the other more complicated situation than the simple discontinuity in the they discovered this numerically, so it's interesting what they did. But to prove that you have this transition mathematically was a big effort, and I would say of which Lorenzo Bertini was the driving force. It was a problem in functional analysis, quite complicated. And this is a paper that we published in the Communications in Pure and Applied Mathematics. So I think this may be a point to stop. Let me see whether I have some conclusions. Okay, so you see, this macroscopic fluctuation theory provides a unified treatment of thermodynamics of driven and diffusing system and fluctuations. And it required understanding both the macroscopic aspects and the connection with the microscopic ones. So this is the formula, the large deviation formula that I showed is like Einstein formula. You can use it in many ways. And it's the borderline between microscopic and macroscopic. And certainly this is, it has been a step. I always consider it the next step beyond Onsager. So Onsager had two strong limitations. He had to be close to equilibrium, and his hydrodynamic equation had to be linear. While here, the hydrodynamic equation can be nonlinear, and you can be quite far from equilibrium. Still, you go through locally to close to equilibrium states, and I think that it could be useful in, not only for the molecular motors, but more in general, in many biological situations where, we live in systems are in more or less stationary states. So, and everything that goes on in our body on a certain scale is a stationary non-equilibrium state. So, hopefully this may be useful. So you see the beginning, because I could not discuss the current fluctuations, but there we found what is the functional that describes current fluctuations and whose singularities describe phase transitions in these current fluctuations. Phase transitions which has been verified numerically and which also represent a novelty, because are phase transitions which break spontaneously time translational invariance, which is also a novelty. And but this I will describe in the lecture. So thank you. Stefano?
Is there a microscopic formula for this quasi-potential V of rho that you can write down? If I give you a system of particles...
well, you can calculate large deviations for a microscopic, but it will be a very complicated object. The good thing about this is that the calculation is purely macroscopic, and you need only macroscopic quantities. So this theory is all you can use as a phenomenological theory.
I have a question about why you said the system is only, your theory is only applicable to diffusive systems. At some point you made the remark that the integral I
Yes.
is sort of generic. And in the next slide you showed that V can be calculated also using as a minimizer of something.
Yes.
So then why is it not?
Well, I think one can go beyond diffusive systems. Certainly one can go to, for example, to reaction diffusion systems. But let's say that we have not studied the more general cases. So
ballistic systems also?
Eh?
Ballistic transport?
Yes, but well, I think...
Euler scaling.
Eh?
Euler scaling. Euler scaling.
Euler scaling. Well, Euler scaling you can get as a limiting process. I mean, if you see there is an external field. If you let the external field to go to infinity, you get the correct results of, at least in one dimension. Then in more dimension, I don't know, maybe you know. Does it work in 2 dimensions?
No, yes.
In 2 dimensions it works.
So I mean, so right now it's established for some class of systems like diffusive systems. Yeah. So can one at least, I mean, is it what that one can expect that in general this one can hope that this will actually give a theory for very I mean the most more general systems like the kind of systems Herbert talked about, like one-dimensional Hamiltonian systems with which have some description of.
Well, the only honest thing I can say is that I have not studied. Let's say that I mean the ideas are rather simple, the basic ideas. So I would hope that they could be extended, maybe with some modification. And there is also the case when you have many components of. And in that case, you may have non-unique stationary solutions, and the situation is more complicated. I think it's closer to what Herbert studied, and the situation is more difficult. I don't claim that this theory is simple to use. Let's say I'm only saying that the conceptual basis is not complicated. But then to use it requires a lot of inventiveness and
Any more questions or comments? If this is not the case, we thank again Giovanni Jona.
Thank you.
Translation.